This is the next example. Let's design a simply supported slab. We have a slab shown in figure is to be designed to carry a variable load of 3 kN per meter square plus 4 finished ceiling load of 1 kN per meter square. The characteristic is 25 kN and we have characteristic strength of steel is 500 Newton per mm square. Basically spin effective depth ratio is 19 for the light concrete slab from figure 6.3, and we have C 25 by 30. Okay, and we have the effective span to be 4.5 meter between the center and support. And first we need to estimate the slab depth. For the estimate of slab depth, for the estimate of slab depth, we need the minimum effective depth, that means span into basic ratio and correction factor. For the basic ratio, this is the figure. Okay, this is the figure for basic ratio. For basic we are going to take 40% of EST, and we have the concrete of 30 25 C25. So we are going to take, it will strike here, this 27. So we can see from the graph. We are assuming the 40% and we have C25. So this graph will strike here, somewhere here. We are going to take we are going to assume the same ratio of 27. 400 span, we have effective span length of 4.5 meter, and we have chosen span by depth ratio 27, and correction factors we have not, but here is SI still being used. The span is less than 7 meter. The correction factor should be taken as unity, so we have taken the 1, and it is also written here. The correction factor account for slabs and support condition as well as case of span greater than 7 meter if it is greater than 7 meter, and for flat slab greater than 8.5 meter. Okay, we need to have if the slab is greater than 7 meter. Okay, and we have taken the effective depth of depth 175 mm, and for class now we need now numerical cover, and for we are going to assume the class X1, so 25 mm, and we have assumed the 10 mm bar diameter, so half 5 meters. So overall the depth of slab will be 170 plus 25 plus 5, means it is 200 mm. Now we are going to calculate the slab loading. Self weight of slab is 200 mm into 25 unit weight of slab, 5 kN per mm square, and permanent load 1 plus 5. 1 is for it is given here for finish and ceiling load 1 kN per mm square, and it is 6. Now we need to calculate 1 meter width of slab, and ultimate load is equals to 1.35 GK into 1.5 QS, means variable load, and we multiply the value and get 56.7 kN. This is the length of span, and this is the width. We have assumed 1 meter. So the movement for the simply supporting WL by 8 means 56.7 into 4.5 by 8 is 31.9 kN per meter. So we are going to calculate the bending reinforcement, and bending reinforcement will be m by BD square by FCK. It is 31.9 into 10 to the power 6 thousand with 170 FCK 25. It is 0.05, and we are going to be lever arm curve. This is the lever arm curve. We have the value K, and we are going to take out really. So we have the value almost 0.044, close to this one. If you take it straight, it will go more than that. That means 0.96 I have taken, and therefore, and we have upper limit. It is written that maximum value of LYZ according consent code when previous you practice 0.95. So Z is equals to 0.95 into D is 1.61, and area of reinforcement will be m by 0.87 Fy kz, and we get the value. And provide S10 bar at 150 mm. We have assumed this, and after that we get how much area of space. So it is in appendix. In the appendix it is here. For 10 mm bar, spacing of bar will be 150. It is 523 mm per meter. Yeah, and we are going to check effective span effective depth ratio. It is del 1 is 100. Area provided, area required by BD, that means 0.26, and minimum area required is 0.13 percentage, so it is greater than that. From the now we are going to check basic span effective brace. 35 means we have got from the figure. Let's see the figure. We have here from the figure. Effective brace ratio is 0. Something, it is given 0.268, means 268 will lie something here, and if you go straight it will be, it is 25 kilonewton we have FCK. Then if we go it will be 32. We have got the 32 value. So this will be 34. Therefore actual ratio for 5000 divided by 170 will be 26.5. Since Susan, our effective depth is okay. 27 is fine. And shear shear will be shear force. We are going to check the shear force. As the slab have little negligible shear force, we are going to check it. Now we need to calculate the shear force at the support, and that station we have the kilonewton 56.7 kilonewton into W by divided by 2 into make the width divided by 2. 4.5 divided by 2 is 2.25 minus, and 300 divided by 2. 300 means width of column, and 2.25 divided by the half of the span, and we get the shear force at the support. Then we are going to calculate the del 1, means the percentage of reinforcement. So 100 into 523 we have provided, 1000 into 1 0.31. So BDR is equal to B. It is from table 8.2. This is from, I'll show you from the concrete table. Yeah, from here it is, we have 0.31 we have. Then it is depth less than 2, we have taken 0.55. yeah. And for concrete modification factor, since we do not need to have modification factor because del 1 is less than 0.4, so no concrete strength adjustment since del 1 is less than 0.4. Okay. And we have multiplied by, this is the shear resistance, and 93.6 in PD. Calculate shear resistance by the slab is greater than the by the to resist by the force, so no shear reinforcement is required because all the shear resistance are resisted by the concrete. Then we're going to calculate the int and coverage, and for the tension we have the table 1 appendix. Let's see 6. Yeah, for here coping length of length cover is given to be, we have FCK 25 and straight bar it is used, and ensuring tension and compression is 40 into bar size, that means 40 into 5, 40 into 400 mm. And distribution part, we have provided the minimum distribution part, that is 13% of BD, and it is right S10 at the rate 200 center to center distance, and this is our maximum bar spacing which satisfy our equation. By this way we can design our simply supported slab. Thank you.